Hi, my name is Bill Kinney, and I'm a math professor at Bethel University in St. Paul, Minnesota. This is an introductory video that I'm making about parametric curves. I'm calling it Parametric Curves Part 0, Introduction. I'm going to make many videos about parametric curves. They are very interesting to me, and I want to help students that are in pre-calculus through multivariable calculus, as well as physics classes, to understand them. So I'll be teaching you about parametric curves, and I'll also be teaching you about Mathematica. What you see right here, this is a Mathematica notebook, and I will be teaching you Mathematica along with teaching you the calculus-related things you need to know about parametric curves, and non-calculus related things too. This will be helpful for pre-calculus students too. I'm saying here that I'm following the second edition of Multivariable Calculus by John Rogowski, but I'm not going in order of the sections in that book. I am skipping around a bit, but I'm using his idea, a lot of his ideas, a lot of his notation, and that's what I teach multivariable calculus out of. So why study parametric curves? This introductory video, I want to try to motivate you, hopefully, to want to study parametric curves and the corresponding parametric equations. And for me, there are two main reasons why somebody might want to study parametric equations and parametric curves. The first is that they are beautiful, and that's actually a very big motivation for me. I study a lot of things in math because I think those things are beautiful, but they are also useful to do many things, and this is what I want to show you in this introductory video, is that they are beautiful and useful. So I've got some examples here. This is in this Mathematica notebook. I can open up these sections that you see here where there's this little triangle on the right there, on the lower right. By double-clicking on this, I can open this up, and I've got some pre-programmed Mathematica code to see things and illustrate why parametric curves are beautiful. You don't have to know this code right now. I will be teaching it to you as we go through these videos. This is just to see what Mathematica can do and to see why parametric curves are beautiful and useful. So I'm going to enter this code right here that we see. And this generates a nice picture of something called the butterfly curve, and Mathematica can be used to animate this. So I'm going to play this here, and we're going to see a curve that looks like a butterfly. I used math to make this curve. In particular, I used functions that you know from pre-calculus, things involving sine and cosine, and e, the number e to a power here, a cosine of t power there. The sines and cosines have different frequencies. Notice there's a t there, a 4t here, and a t over 12 there, and you've got this power, this fifth power there. I found the equations for this butterfly curve from this article here in the American Mathematical Monthly. So that's kind of pretty, and Mathematica was used to color it in an interesting way using this command right there, color function arrow rainbow in quotes. I am very interested in geometry, and including three-dimensional geometry. I like thinking about spheres and tori, the plural of torus. A torus is more commonly known as a donut. You can make curves that lie on these surfaces, and that's kind of interesting. So let's see what this looks like here. So here we have a sphere, a ball, which was really the surface of the ball, and I use trigonometric functions to put a parametric curve, a curve that is parameterized, I'll talk about what that means in later videos, to fill up the sphere in an interesting way. And one thing we might want to figure out is, why is this curve on top of a sphere? Somehow these equations that I have here result in a curve that's on top of a sphere. Likewise, I made a curve that was on top of a donut. Again, the official name for that is a torus. By the way, you can, well, I guess you noticed you can rotate these things in Mathematica too. Here I got a curve that lies on the surface of this torus. There it goes. It's a pretty picture. But again, we might wonder why. Why does it lie on the surface of this torus? Somehow these functions that you see in here are generating a curve that lies on this torus, and it would be an interesting thing to try to figure out why. You can parametrize the intersection of two surfaces. Sometimes when you've got two surfaces, it's hard to see where their intersection is. In this case, I've got this cylinder and this, I believe it's called a hyperbolic paraboloid or something. This other saddle-like surface. Where do they intersect? They intersect along this red curve there. And that can help parametric equations and parametric curves can help you see that. They also form the basis for forming other kinds of surfaces. This kind of surface is interesting. I made this by using a parametric curve and using what are called normal vectors to the parametric curve to generate this surface, which kind of looks like a duck quacking or something. Kind of an interesting looking thing. Parametric curves are useful as well. I used to like, when I was young, playing an old Atari 2600 video game called Basketball, Atari Basketball. The graphics were horrible, but it was a lot of fun. This code here generates some graphics that remind me of that old Atari game that I used to play. You've got kind of like a stick figure there. Actually, I think the Atari ball was square instead of circular, so I at least made my ball circular. Here we've got parametric curves being used to model the motion of a basketball under the influence of gravity. I can change the initial angle that I shoot the ball at. I can change the initial speed and see whether it goes through the hoop or not. You can also model planetary motion. This code does that. It uses some differential equations to model planetary motion. And so what we have here is a little toy solar system. I've made the Earth, you might say, blue, and Mars red. These orbits around the yellow sun are more eccentric than they are in reality, but it's still interesting to look at anyway. If you know anything about Kepler's laws, these planetary orbits are following Kepler's laws essentially, though there's a constant of proportionality in one of those laws that's going to be different here for this toy solar system. Hitting a target, this code right here makes, well, I tried to make the thing right there kind of look like the Starship Enterprise, but I failed at that. But anyway, this thing right here is flying through the air and shoots that target. We can use Mathematica and parametric equations to generate parametric curves that illustrate this. And that's kind of a fun thing to do. And finally, I use parametric equations and parametric curves a lot in studying differential equations. What this picture shows is something called the flow for a system of differential equations, and the solutions that follow the flow lines are examples of parametric curves, and here you can see all these curves going in toward the origin. So that's my introduction to parametric curves. I hope I've enticed you a little bit to want to learn more about them, and in many future videos I'll be going into lots of detail about them.